Are you the kind of guy who just sort of hacks things until you figure out how to make it work, or do you actually try to like do you read all the docs? You like go through a tutorial on any new framework that you're trying to learn, or what's your approach there?
Probably a mix of what you just said. I think it's like I think I usually go through tutorials on things. I don't usually read the docs until I need to like find something. So I think you usually have a sense of like what's in a particular package, on whether it will be there or not, and then you can look at the docs when you're actually trying to implement something. I think I've learned a lot more about software design, I think. Coming from a physics background, I didn't really appreciate properly the benefits of modularity and like how to structure your code and how to work on large code bases, and like why it's a bad idea to mutate variables and things, like things that seem quite superfluous if you're just hacking together like a script for physics or whatever, just some kind of experimental thing.
For sure.
But then when you work on a large code base, you notice that, if you have a mutating variable somewhere, then 3 months down the line, it's definitely going to cause a bug and someone's going to have to fix it. And it gets very annoying. So you focus a lot more on trying to design systems well. And I noticed that one thing that was actually quite important is you have to design software which maps to your conceptual models really well. And if you have a conceptual model of an object or whatever it is, and it can't do the same thing in code, then you end up having to hack around it and be like, oh, we can make the code do this weird thing, which then makes it look like the thing in real life. And then you just start running into lots of trouble because...
It is in some sense another kind of mental bookkeeping. It's having an idea, again, not just symbolically, like what are the different variables, but in memory, what are the different things that exist? How can they be manipulated? How persistent are they? It's just very, very large scale algebra in a sense.
And it can be done well and it can be done badly, I think. The strange thing about software engineering is that you don't get told if you're writing bad programs, I think, immediately, like in the sense of there's not that much feedback and it only comes later on. And so you see the benefits
and so much of the challenge of large scale software engineering is about sort of, well, honestly, it's like running the British Empire. It's just bureaucracy. It's having a good system for code reviews and having taking the time to write good design docs and actually think things through carefully, which is not a skill that I have.
Which is why the label of like architect seems to make more sense, I think. I think it was Microsoft that originally started like software architect. And I think when you take it seriously, you do see the importance of like good architecture, because making a bad decision early on can just really screw you over later on in terms of your data structures and things
but it's architecture that you can't visualize in the same way.
Yes, exactly.
It's architecture in symbols instead of in building material.
You can draw lots of flowcharts and things. There's actually another question I have is, so when I was young, like 15, 16, and was reading about the scientific revolution and this kind of the Enlightenment and rationality coming up as a way of thinking. One idea that I had quite a lot, which is, okay, so in the 1800s now we know all of these things using the scientific method, and Galileo has taught us all these things. And we're as confident in our beliefs as people in the 12th century were about their religious beliefs. And so they believe that true knowledge comes from scripture and from religion and things like this. And we believe that it comes from science and thinking things through. Then just kind of by inference, this is a terrible argument, very hand wavy, but surely there must be some other thing that comes next, which is, all those weird mathematical calculations that we were doing, they were fine for where we were in our evolution of science. But there will be something new. And I guess Stephen Wolfram has this argument about a new kind of science, which is a little bit overblown, but it's kind of
some of that self-promotion.
But it's essentially this idea that like the mathematical tools that we have for physics in the like 18th, 19th, 20th centuries were great, but really it's going to be supplanted by computation, and computation is the kind of new mathematics of problem solving.
Well, I mean, I don't agree with him that cellular automata will be the new foundation of all science, but the idea that computational science is kind of a third way of doing science that's neither really experimental science nor theoretical science, in the sense of like coming up with theories and like scribbling equations on again with quill and parchment, that I do agree with, and that actually was a big revelation to me, and part of what led me on my current path, where I really do think of myself neither as an experimental nor a theoretical scientist, but as a computational scientist, essentially writing simulations of model systems, and sort of picking the right model data and running sort of experiments with code rather than either strictly calculating things or testing physical things.
That's interesting. It's interesting that you choose simulation and this idea of running experiments, because one other way to view computation is, just a really great calculator, where now if I can't find algebraic solutions to my complex integrals, then I have a numerical solution available.